All right, so welcome to the next semester of LaACES, the second semester. And during this semester, there's going to be a lot more independent work. In fact, what you'll be working on is going to be the developing a flight payload that will eventually fly up to 100,000 foot altitude. So a lot of what you're going to be doing here is working on a flight project, just like a true NASA type program, though in a much more mini scale. And so a lot of what will happen this semester, you're going to use the skills that you developed last semester, but you're going to be working as a team. And you're going to have to understand things like team management. Remember those written documents that you did last semester? Well, it's going to get much worse. You're going to have like real documents for your flight that are going to have to be developed through this. So we'll talk about what these things are going to be this semester. So we're initially starting off with some of the project management type things. Project management many times is referred to as the art of risk management. So you're going to be learning how to actually control your project and be able to produce things on time at high quality. That's going to be one of the major efforts. Then the other hard activity that you'll be engaged in is going to be the construction of the megasat. This is going to involve slightly different soldering techniques. You're going to be doing surface mounting soldering with the megasat, and that megasat is going to be the core of your payload that eventually you'll design and develop and fly. We'll be doing a calibration, a thermal vac test in April. You're going to have a flight ready payload, and then you'll be here at LSU, hopefully. And we will run both a vacuum and a thermal extreme test on that payload to determine whether or not your flight payload will be actually able to survive and produce good data during the flight. A balloon payload is what you're going to construct. It's going to be like this. It's going to be limited to 500 grams of weight. It's going to have dimensions roughly something like 15 centimeters to 20 centimeters on a side. There is a interface. You're going to be learning about interface control documents and interfaces. And the interface that you are going to have to the flight vehicle are going to be two holes that pass through your payload unbroken with a string that is 17 centimeters apart. That is what the interface to your flight vehicle. So here's these strings coming through the payload, and then we have clips on the top and the bottom that hold your payload in place relative to the other payloads. By May 2022, you're going to have a payload that is designed, built, tested, and shown to be fully flight worthy. You're going to have to complete 3 major design reviews and that thermal vac test. Once we fly, you're going to have 48 hours after the flight to analyze your data and prepare a science presentation. If we, hopefully, COVID will allow us to return to our normal flight operations, where we go to the NASA Columbia Scientific Balloon Facility in lovely Palestine, Texas, and be able to fly the balloon payloads from there. CSBF is the worldwide center for the NASA Scientific Ballooning Program. These folks put up 6,000-pound payloads with balloons that would fill large football stadiums, and they do it all over the world. They do it out of New Zealand, they do it out of Sweden, they do it out of Antarctica. So these are the professionals, and you're going to be presenting your science result to this group of professionals. So the word of warning here is make certain that not only is your payload ready, but your flight software and your ground data analysis software procedures are all ready as well, because you only have 48 hours to get that done. So the core of your payload is going to be the Megasat. That's what this is shown in through here. You've already worked with the Arduino Mega, the CPU or the brain for your payload, and you've already worked with the ultimate GPS unit, which has the SD card and the GPS unit built in. You've already worked with those, and you've already interfaced detectors with it. This Megasat, by some miracle, has sensors very similar to what you did for your capstone last year. It has 2 temperature sensors, a humidity sensor, a pressure sensor, and I think we've got 2 gain ranges on the pressure sensor this time. A 3-axis accelerometer, a 3-axis gyroscope, and a real-time clock with a battery backup. That's what's all on this board, and it stacks together with your Arduino and your GPS. So by itself, this one is a real nice self-contained little payload. This prototype area in your GPS unit, you can use that to put in your sensor interfacing for things that you want to do to expand what you'll be working on. Or you can get a proto shield that will just snap into your bus here to produce your interfacing. So once we're done sort of with the project management, you're going to want to get and start working on the assembly of the Megasat sealed and get all that group. In the meantime, while that is all going, you're going to have to be preparing for your preliminary design review as it goes. So you need to take this time that you're working on the Megasat into account in your project schedule. So there's several things, there's many things that you could potentially do with this system and other things, like, for example, measuring radiation intensity as a function of altitude, or things like looking at ultraviolet as a function of altitude. Remember that ozone is directly related to ultraviolet. First of all, UVC is blocked by the ozone. That's what the good ozone is doing. But the UV also produces ozone in the upper atmosphere. So measuring UV would give you an understanding as to where the ozone layer is. You can also, there are various sensors for different gases that you could interface into attempt to measure. Airflow. There's not a lot of air at 100,000 feet. In fact, the pressure at 100,000 feet is pretty close to a percent of what it is here on the surface of Earth. So trying to measure the flow of that air can be very difficult. There's various methods that you can do to do that. Atmospheric temperature. That is just measuring the atmospheric temperature is a non-trivial operation. Temperature measurements are affected by lots of different things. They're affected by heat being radiated from your payload. You can get very different temperature measurements depending upon what the color of your sensor is, whether or not that it's exposed to the sun or not, et cetera. So there's a lot of different things that you'd have to do in order to get a real accurate measurement of what the ambient temperature is. Then there's things like boundary layers. So as your payload goes up through the atmosphere, there's a certain envelope around that payload that will change as you move out from the payload, all the way from the flow of air around the payload immediately to it, to farther away, which will be less affected by thermal effects and other things. An inertial sensing system. You've got an accelerometer and a gyroscope on there. You can attempt to try to use those to to determine the attitude of your payload as a function of time. So there's a bunch of different things that you could potentially do. There's an online lecture 18, number 1, that provides even more details about various things. The other thing to keep in mind here, and in fact, you should be starting to think about this, is that there is the 2023, the fall 2023 annular eclipse and the spring 2024 total solar eclipse. These are the paths of totality on it. LSU, our group, will be involved in this. We are working with Montana State University, as we did in 2017, to lead a group of teams to these solar eclipses. However, if you want to participate, you're going to have to win the 2022-2023 solar eclipse competition. So next year, starting next year, we're going to be looking for competitors who want to try to go to this solar eclipse, and they're going to have to come up with a payload that would fly, that would be appropriate for a solar eclipse, and we will judge them based upon a number of criteria in it. So those kinds of details will be coming up before, but we'd be looking at 2 trips. We'd be looking at annular trip on October 14th, 2023, and then the total eclipse in April 2024. Both trips we'd probably be going to the middle of Texas for, is where we would go for this thing. There's a National Eclipse Ballooning Project. There's a link over there that you can look for more details about the actual eclipse ballooning project. This competition that we'll have next year is going to be, I think, in addition to what's on the National Eclipse project. So you can look at both of those things, and you can get some better understanding about some of the other possible experiments that you could do. So this year is the year to start thinking about this, all right, as to how you want to proceed with the competition. You're going to have a team. So any sort of complicated project, as we're going to talk, is going to have to involve a teamwork. And so one of the exercises that you'll start today is going to be developing your team contract. This is your rules of engagement in terms of how you're going to actually operate as a team. You need to write down, with your team members, not your faculty member telling you what to do. Your team members are going to have to figure out how you're going to engage and write that down. That'll get reviewed by your faculty advisor, and there'll probably be some constructive discussion about it. You probably go through 2, maybe 3 iterations of this before you get something that is close to being operational. This is not something that the official LaACES program wants to see. We don't care. This is internal to you. If you have a good management, if you have a good project and a good team operational, then we'll see that in your preliminary design and your critical design and your flight readiness review documents. If you don't, then you're going to have a lot of troubles with getting those documents completed. So make certain you spend the time on this, and faculty advisors, make certain that you also guide them as they're going. As we did last semester, all of the lectures and the activities are online on the student ballooning course in LaACES, so you can look at all these things in advance. The only thing that is going to be a little bit different from this cycle is that next Tuesday, we're going to start with the system design and then go into requirements, rather than the other way around. So that's the only difference here that I see with this. And then there's a number of things with design of the balloon vehicles, flight profile, thermal design, battery systems, et cetera, that we're not going to go into detail. That material is available and you probably want to review it. Particularly things like constructing the mechanical payloads out of foam, the cube payload or the LaACES octagon. This is important. It will give you a good insight as to how to put together a payload. Throughout this semester, there's going to be some evaluation of your work through a series of 3 major reviews: the preliminary design review, the critical design review, and the flight readiness review. And I'll go through exactly what these things are with the next lecture. We also include a preliminary PDR and a preliminary CDR. And we recommend that you do the preliminary PDR and CDR at your institution. We do not need to see any outcomes of those preliminary reviews. The LaACES management only wants to see the completed PDR, CDR, and FRR documents. These documents, once your team at your institution puts these together, those documents need to be fully vetted by the institution faculty advisor. So you need to plan accordingly. We will have particular due dates that we need these documents here. So you need to make certain that your faculty advisor has those earlier and has a chance to review it so that you have a chance to fix the problems. We're going to be very, very serious about these documents. They're going to be graded as pass-fail. If you have a fail on any of these documents, it's very likely you will not be allowed to fly. So take these documents seriously, put the time in, make certain you get appropriate input from your faculty advisor, incorporate your faculty advisor's input, and everything should be doing fine. Templates for all 5 of these documents are on the LaACES website. There's the link for it. You can go look these things up. These documents build upon each other. So I'd say that, yeah, these documents build on each other. So even though we don't require to see the pre-PDR, do I say that in there? No. So even though we don't require it to see the pre-PDR, you need to complete that. Complete the pre-PDR template before you go on to the PDR template. A lot of what you see review these templates. A lot of what you'll see in these later templates is this was already done by a previous document, just cut and paste into here. The other item to be aware of is that these can be pretty extensive documents. It is not unusual for a FRR document to be 80 to 100 pages long. All right. Here's your schedule. I did not include anything in here about team contracts or pre-PDRs or anything. These are the dates that we want to see the documents returned to LaSpace. So the PDR document, we need to see that delivered February 18th, 2022. The CDR document, April 8th. We'll be having thermal vac testing at LSU April 22nd. And then your final FRR document will be due May 6th. Currently, we are planning to have the flight launch trip May 15th through May 20th, 2022. That's the current plan. And your defense of that will be at CSBF May 16th. That's our current plan. And we'll probably make a final decision about this. What are we doing? March-ish? Yeah. March will be our final decision as to how we'll proceed with this.